welcome to our channel Helm of Science. So in my previous videos I had been discussing about the chapter force and pressure. So now in this video I'll start a new chapter which is heat, and it's one of the most important chapters of class 9. So before starting this chapter I would be discussing about two terms which are quite interrelated but not at all the same. So now heat. Heat is generally it is actually form of a form of energy. Now many students, like, they get confused between the terms heat and temperature. Heat and temperature are quite related, like heat and temperature are related, but they are not the same. Temperature is, now I discussed that heat is a form of energy, but temperature on the other hand is a measurable quantity. Like we can measure our body temperature with the help of a thermometer, right? So it is actually a measurable quantity. It is a measurable quantity which can be measured with the help of a thermometer. But on the other hand, can we measure heat with the help of any instrument? No, right? So what do we mean by heat? Now we know that any object is made up of matter. It is made up of molecules. Like say this is a body, the square shaped object. It is made up of molecules. Now these molecules are free to rotate, like they are free motion, they are free random motion, right? Now body object has two types of energy, like the molecules inside an object has two types of energy. One is the kinetic energy, which is due to the random motion of the molecules. Other is the potential energy. This energy takes place due to the interaction between the molecules among themselves. Interaction, this energy is there due to the interaction of the molecules. Now the total energy of the object, rather we can say that the total energy of the molecule is equals to the addition of the kinetic energy and the potential energy. Now if we take into consideration all the molecules, then the potential energies of all the molecules and the kinetic energies of all the molecules are added up to give the total internal energy. Taking into consideration all the molecules, if we add up the energies, it gives the total internal energy, which is nothing but the thermal energy of the object. Now more the thermal energy, more will be the temperature. Now if we say that, like, take into consideration an body A, which is denoted by A, it is a hot body, it's a hot body. So thermal energy will be much more in case of the body A. Thermal energy will be high for body A. Now if we take another body B, it is a cold body, this is cold, so temperature is less in this case, in this body, and the thermal energy is also less as compared to body A. So thermal energy will be less. If we take another body, body number C, which is even colder, so with respect to body B, this body is even colder, so the temperature of this body with respect to body B will be much less, and the temperature of this body will be much more with respect to the body C. So we can tell that a body has more thermal energy with respect to another body. So in this case, while if we compare between A and B, its thermal energy will be less. The body B's thermal energy will be less. But if we compare it with body C, its thermal energy will be more. So colder, the body C is colder, so thermal energy will be even less for this body. Thermal energy will be even less for this body. Now if we join body A and B together such that this thermal energy can flow from body A to B. So what will happen, as it has more thermal energy, some of the energy will transfer from body A to body B. This transfer of thermal energy, from a body at high temperature to a body at low temperature, which is body B, is nothing but heat energy. Thus when a body is at higher temperature and a body is at cold temperature, like lower temperature, so there will be a flow of energy from the hot body to the cold body, and this energy is nothing but the heat energy. So this is very important like concept which you have to keep in mind, and all the topics in the coming future will be based on this concept. So as I discussed, heat is a form of energy. So the SI unit of heat will be nothing but units of heat. SI unit of heat will be nothing but joule, denoted as J. CGS unit is erg, and the relation between joule and erg is 1 joule is equals to 10 to the power 7 erg. Now another common unit in which heat is expressed is calorie. It is denoted by CAL, and also kilocalorie. Now the relationship between a calorie and joule is 1 calorie is equals to 4.186 joule, which is almost equivalent to 4.2 joule, and 1 kilocalorie equals to 1000 calorie. Now what do we mean by calorie? Is a very important part. Often questions are asked that what do you mean by 1 calorie? Now I have taken a container here and we have filled it up with 1 gram of water. Now 1 calorie is defined as the heat required to raise the temperature of 1 gram of water by 1 degree Celsius. To raise the temperature of 1 gram of water by 1 degree Celsius. So, and the raise in temperature by 1 degree is like, it is noticed that it is done when it is raised from a temperature of 15.5 degrees Celsius, sorry, from 14.5 degrees Celsius to 15.5 degrees Celsius. Why we take 14.5 to 15.5? It is another concept. It is due to the abnormal behavior of water towards expansion and contraction. We will discuss in the later video. So just for now, keep in mind, when we require to like raise the temperature of 1 gram of water by 1 degree Celsius, which is from 14.5 degrees Celsius to 15.5, which is preferably from 14.5 to 15.5, that amount of heat is known as 1 calorie. Now, the next topic is thermal expansion. Now we know that most of the object materials expand on heating. I am specifying most of the objects because there are some objects, some materials which has like unusual behavior towards heating and cooling, and we will discuss it in the next video. So most of the objects expand on heating and contract on cooling. So when we increase the temperature, they expand, their volumes expand, and on cooling their volumes, they decrease, the volumes decrease, so they contract. Now for solids there are three types of expansions. When there is an increase in the length of the solid, that is known as linear expansion. If there is an increase in the area of the solid, it is known as superficial expansion. And if there is an increase in the volume, it is known as cubical expansion. These three types of expansion takes place in case of solids. But however, in case of liquids and gases, as they don't have any shape of their own, there only exists cubical expansion. They can only expand on in volume on heating or cooling. Cubical expansion. One thing which has to be kept in mind is that expansions in case of liquids is more than in case of solids. So in expansion in solids is less as compared to expansions in liquids. And again, if we compare between liquids and gases, the expansion of gases is even more than case of liquids. So expansion in gases is much more in case than the liquids. So we'll come to linear expansion. Number one is linear expansion. Now, if we keep a rod and we heat it by some amount, so there will be linear expansion of the rod. The rod will increase in length. So this increase in length depends on the following factors. This is the material of the rod, material the initial length of the rod, it is seen that if we take a rod of 2 meters of iron rod and a 4-meter iron rod, the 4-meter iron rod will expand much more. So it depends on the material, the initial length, and also the rise in temperature. Rise in temperature. Now, so the increase in length depends on these three factors. Now let us consider the length of the rod at initial temperature. Let's say length of the rod at temperature 0 is the length at initial. Length at initial. L0 is the length at initial temperature, and length LT is the length at final temperature. So increase in length, let's rub this off. Increase in length, which is LT minus L0, LT minus L0 thus is directly proportional to the initial length, which is L0. LT minus L0 directly proportional to the initial length, also the rise in temperature, which is T. Thus if we combine these two, we get LT minus L0. If we get rid of the proportionality term, we will introduce a constant of proportionality alpha, L0 T. Thus the equation becomes LT minus L0 equals to alpha L02, where alpha is nothing but coefficient of linear expansion, where alpha is the coefficient of linear expansion. This formula is very important for solving numericals which come from this chapter. So we can also say that LT equals to L0 plus alpha L02 T. If we take L0 common, 1 plus alpha T. This is also one of the most important formula, and also from here we can say that alpha equals to LT minus L0 by L0 T, that is the increase in length, increase in length by initial length into the rise in temperature. These three formulas you have to keep in mind to solve the numericals. Now we'll move on to superficial expansion. Number 2 is superficial expansion. Again, the rise in temperature, or no, sorry, the rise in area, increase in area. Similarly, like the linear expansion will depend on the material, the initial area, and the rise in temperature. So just like the case of linear expansion, these the increase in area is dependent on these three factors, and just like that we can solve that the increase in area, let the area at initial area, this is initial area A0, and AT will be the final area. So the increase in area AT minus A0 becomes equals to beta, the initial area which is A0 and the rising temperature T, where beta is coefficient of superficial expansion. We can thus from this we can derive that beta equals to AT minus A0 by A0 T. Also AT equals to A0 1 plus beta T. We have derived these three just like the case of linear for superficial expansion. Similarly, for cubical expansion, will have the same the factors on which cubical expansion will be similar to that of the linear expansion and the superficial expansion, and the relation will be the rise in length, rise in the volume will be Vt minus V0 equals to, it will be dependent on gamma V0 T, where gamma equals to coefficient of cubical expansion. It is also seen that the relationship between alpha, beta and gamma are alpha is to beta is to gamma is equals to 1 is to 2 is to 3. So these were the three types of thermal expansion seen in solids. So this will be it for this video. So see you in the next video. If you find this video useful, please like our video and share the video and subscribe to our channel. Thank you.